We looked at, so we'll look at a little bit more about noise. So we've been looking at noise for the last 2 classes. We'll do a little bit more about noise and look at noise performance of some common circuits. So last class we just took a resistive network and looked at the input referred noise sources. So let's take a couple of examples from the, of MOSFET based circuits and look at them. But before that, I just wanted to point out one thing about flicker noise, right? So before we get to that. So let us just take a look at what happens when you look at integrated flicker noise. So if you take a MOSFET, you have 1 over F noise at very low frequencies and flicker noise, right? So suppose you're going to integrate this 1 over F noise to find the overall noise in a particular frequency band. What is this? The expression for this is K times K over F GM squared WL Cox squared delta F, right? Now one more thing to note, there are actually different expressions, okay, several ways to express this. So if you use a different empirical constant K, because Cox, remember, is a process based constant, okay? So you can actually give a different empirical K and just call it K over F GM squared over WL Cox, for example. There are many ways of expressing this. Different people like different expressions. Okay, I just happen to use this, that's all. Okay, so you can actually, I mean, if you look at Razavi's textbook, the analog CMOS textbook, he actually uses K over F GM squared over WL Cox. Okay, it's just a different constant, empirical constant, that's all. So suppose I'm going to integrate this, okay, from a frequency F1 to F2. What is this? I'm going to integrate this from F1. Okay, let's go to the next page. F1 to F2. Oh, sorry. Okay. So if you integrate 1 over F, you get ln F. From F1 to F2, you get ln of F2 over F1. Okay. So what does this actually tell you? If you look at actually, let's say if you look at 2 decades, okay, of frequencies. For example, if you integrate from, let's say 100 Hertz to 1 kilohertz, and if you integrate from 1 gigahertz to 10 gigahertz, the overall integrated 1 over F noise is going to be the same. Okay, that's actually an interesting property. Okay, so you have a 1 over F noise, the magnitude keeps decreasing, but you're integrating it over a wider bandwidth. So the overall integrated noise tends to be the same. Okay. So that is one interesting property. Now a few days ago somebody had a question, what happens, if if you keep reducing the frequency, right? If you keep observing lower and lower frequencies, obviously that means that you'll need to increase your observation time. We looked at that. You can actually calculate, okay, what will happen if you assume a certain observation time and see how much extra flicker noise you add. Right? Now that we know that it depends on the decade, right? Every decade you add extra noise. Now you can find out. Okay. So for example, let's take the case. Let us say let's say your observation time was 1 day, which is actually quite long, right? If you want to look at DC, you would typically never do that. It'll be in, maybe seconds, right? Or maybe tens of seconds. Suppose you take the observation time to be 1 day. Okay? So that happens to be 86,400 seconds. Okay? So the frequency corresponding to that, 1 over 86,400, happens to be, okay, 1.16 into 10 power minus 5 hertz. Okay? So let us say we want to find out the number of decades from, let's say, originally you are going to integrate from maybe 100 hertz to 1 kilohertz or something like that. Or 100 hertz to, doesn't matter, you can take any, let's say 100 hertz to 100 megahertz. Okay, how much is that? 6 decades. 6 decades, right? Let's say originally you are integrating from 100 hertz to 100 megahertz. Now you are going to increase your observation time such that the lower end is going to move to 1.16 and 10 power minus 5 hertz. You want to find out how much extra flicker noise you add. How do you do that? So let's take the number of decades from we'll first calculate the number of decades from the frequency corresponding to 1 day to 100 hertz. And this happens to be 7, right? Approximately 7. What is the number of decades going from 100 hertz to 100 megahertz, your original one? That's 6. Okay? So your original integration was 6 decades. Okay? Your new integration is 13 decades. Okay? So now let us say you have the expression for the current, right? Integrated noise. You're going to find out the ratio of the two to find out how much it's increased. What will you find? Now remember that now we are interested in amp per root hertz. So that's the noise current. Okay? Everything else stays the same. This just happens to be root of 13 by 6. Okay? How much is that? Approximately 1.47. So even though you have pretty much, decreased the observation time, the lower end from 100 hertz to 1e minus 5 hertz, you've just added 50% more in flicker noise. Okay? Which is, not that large as you would expect. In other words, if you actually decrease it even further from 1 day to 10 days, for example, it's really not going to change that much. Right? If you increase time from 1 day to 10 days, you go from root of 13 by 6 to root of 14 by 6. Really not a lot, right? So that's what this shows. So in a practical system, you don't have to worry about, beyond a certain point. You're never going to observe in terms of days anyways. It's all going to be in terms of seconds. Okay, so this means approximately 47% more noise. Yes? Actually, it's not, right? What does DC mean? To observe real DC, you have to observe for, you have to average it over infinite time, right? Can you ever do that? You always have a practical cutoff. What does DC mean? You really have to, right? What do you mean by it will stay at some particular value? You'll know it stays at some particular value only if you, observe it for such a long time. Take a simple RC. So let's say you have some, you have a DC couple, AC coupling cap, right? In reality, in a real system, the output side will eventually, it will settle to the DC what is set by something else on the right side. Okay. But in reality, if you really want to settle to the DC, you'll have to wait for infinite time. It's an exponential, remember. Any settling phenomenon is an exponential. So if you really want to observe the DC, you have to, what you can say is that compared to your time constant which you are interested in, your observation time is large enough such that you can assume it's DC and move on. Okay? That much you can say. Okay? Okay? So that's for flicker noise. So this is just something interesting, I think, because somebody talked about. I think you were the one who asked about infinite flicker noise, right, at DC. Okay. So now let's come back to your thermal noise. So you'll see that quite often one of the properties of this is that because it keeps going down with frequency, what that means is if you're really interested, let's say if you're integrating noise from 100 Hertz to 100 megahertz, okay. Typically what you'll find is 1 hour of noise will not be a major portion of the noise, okay, because your 1 hour of, beyond your 1 hour of noise corner, your 1 hour of noise goes below your thermal noise floor, and you're going to be integrating thermal noise which is much larger, okay, and in a typical broadband system 1 hour of noise would be of less concern than in a narrowband system, okay. Okay, so we know that the total noise at the output, okay, that's going to be, you're going to have a component from flicker noise, okay, you're going to have a component from thermal noise, that's fine. How about this guy, RDS? Are you going to have 4kT over RDS squared? 4kT over RDS delta F? What do you think? Why not? If yes, why? If not, why not? Anybody? Okay. 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 Suppose now if I look at a case where let's say RDS is small, let's say I use a minimum length device, right? RDS will be pretty small. Actually, if you look at some of these short channel devices, let's say if you take a 60 nanometer or 90 nanometer device, your RDS actually can be just a few kilo ohms. It's not very large. Anybody? So okay, see, remember RDS is not a physical resistor. You're using it to represent channel length modulation. So it's actually a virtual resistor which is used to represent, right, dou ID over dou VDS or 1 over dou ID over dou VDS, right? So it's not a physical, resistor which produces noise. Okay, so in reality RDS does not produce noise of its own. Okay, just remember that. I don't want, suddenly if I give a circuit in the exam and one of you suddenly starts putting in noise sources for, for RDS, just remember this. Okay. Yes. How do I? Yes, what about this? No, this is thermal noise current. Okay. Let me has two components, okay? So this GM times, okay, so maybe that's the problem is my notation, okay. I should be careful about this. What is this source? It's a voltage controlled current source, okay. Whatever noise, whatever voltage you have here, whether it's noise or signal or anything, that gets converted into a current which is GM times VGS. What is this? This stands for the noise source. This stands for noise plus signal. This stands for just the noise alone. Okay. If you didn't have a signal here, let us say you have a common source amplifier with this grounded, and you're applying the signal directly without a source resistance, you would short this to ground. What is VGS? 0. Therefore, this signal goes to 0. You will still have thermal noise. Right? The noise is independent. So, the noise is something added extra. So, this is basically the small signal, low frequency small signal model of the MOSFET with noise included. Okay? So, and the noise is going to have two portions. One is the thermal noise, which depends, is 4 kT gamma GM delta F. The other is the 1 over F noise, which happens to be K over F GM squared over WL Cox squared times delta F. Okay? In a general case, you are going to have both. Okay? How about bipolars? Let's take an NPN. Remember that we talked about diode noise, right? Noise in a diode called short noise, which was 2Q ID delta F, where ID is the current through the diode, right? So, in the case of a bipolar, you have you have two sets of noise sources. One is the noise through the base emitter junction, which is IB squared. The other is IC squared. Okay? IC squared is just 2Q IC delta F. Okay? And if you want to express it if you want to express it differently, you can put in GM is nothing but, if you want to express it in terms of GM, for example, GM is nothing but KT, IC over VT. VT is nothing but KT over Q, right? You can rewrite this slightly differently. So you can rewrite this as 2 KT GM delta F. So this brings it to the similar form as what you have for the MOSFET. Okay? And similarly, IB squared is nothing but 2 KT times GM over beta delta F. GM over beta is 1 over R pi. If you want to express it in terms of R pi, you can call it 2 KT over R pi delta F. Okay? Well, it flows through the collector base junction, but eventually that current also flows through the emitter, right? No, that eventually flows through the, see this collector current, right? If you look at a transistor, it flows through the base and eventually flows through the collector. Okay? So it's perfectly fine to connect it between the collector and the emitter. Okay? That noise eventually does flow through the emitter. And one more thing, these two noise sources, okay, so normally in a bipolar transistor, IC is beta times IB and so on, but it turns out that these two noise sources are actually statistically independent. So they are not correlated. Okay, even though it looks like it's just one is just, beta times the other, they're actually not correlated. Now there are other noise sources which we may cover this in a tutorial, but typically a bipolar transistor has other, it actually has a base resistance, a physical resistance, base resistance RB that produces noise. So that is also a fairly significant source of noise in BJTs. Yes. Yes. Yes, but it's not, okay. The dependence of the noise, the power spectrum density of the noise is proportional to the DC current. And that is the reason why we are writing IB as IC over beta. Okay. However, the source of the noise itself is not correlated. You understand? It's because of the DC current. Okay. In the other case, it's because of the DC current, which is IC. However, I mean, the only reason why we are able to write this as GM or, I mean, IC or beta here is because we know the two DC currents are related. Doesn't mean the noises are related. Right? No, unfortunately, we don't have time to go through it in this course, but the sources of the noise are actually independent. They are not dependent. Okay? So similarly, a bipolar transistor also has flicker noise. Okay? And again, you can write some expression. It will look something like this. It will be, some function of the base current and, some empirical, factor K1. Bipolar transistors also have a 1 over F noise. But what you will find is, usually K1 is small enough such that the flicker noise in most cases can be neglected. Not all cases, but basically what I am saying is the flicker noise in a bipolar transistor is much smaller than that in a MOSFET. Okay, and typically the flicker noise corner will be much lower. Okay, in which case you would quite often neglect the flicker noise. Okay. Okay, so let's now look at start looking at input referred noises of some typical circuits. So let's start off with the common source stage. If you have to write this expression, what would it be? Easy way to do it is calculate the output noise current, right? The current flowing through the output node multiplied by the output impedance, which happens to be, in this case, you can neglect RDS with respect to RD, so it's just RD. Okay. So from this resistor, you have 4 kT over RD, that is one noise current, correct? Plus flicker noise, okay, plus this is the sum of the noise currents, powers, right? So you have to multiply it with RD squared. Okay? What is the voltage gain? Minus GMRD. So now we want to find out the input referred noise voltage. Right? 1 over AV squared. You're going to have 4 kT gamma over GM from the thermal noise. This GM squared vanishes. Plus 4 kT over Gm squared Rd. Okay. So what does this tell you? This is the input referred noise voltage. Okay. So normally we want to, this is, this tells you how much noise the circuit is actually adding. Right? Suppose you want to minimize this noise. What would you do? First of all, how would you minimize flicker noise? Same as before, right? Increase the length and width, increase the area of the device. So this one, there's really not a, certain amount you can do and that's it, right? Okay. That you can increase the area. How about the other two? Increase GM, right? That's the obvious thing you can do. So what that means is the larger the GM, the lower the input referred flicker noise. Lower the input referred thermal noise. Okay. So in other words, if you want a low noise design, you will have to increase GM. Okay. Suppose you are using the same common source as a current source. Okay. Now what would you do? What is the output noise? Suppose you are using the current source into an amplifier as a bias for an amplifier. Okay. What do you need to do? You actually now need to minimize the noise current here at the output. Here there is no longer talk of any input referred noise. Because it's a bias going directly into the amplifier, you have to minimize the noise here. What is the noise here? 4 kT gamma Gm delta F. So if you are using a transistor as a current source, you want to minimize the Gm to minimize noise. Okay, is that clear? Again, let's do an example. Let's, stop talking about flicker noise for some time. We'll just consider the thermal noise. Okay. Okay. This is the total noise current at the output times the output impedance. RDS1 parallel RDS2. Right? What is the voltage gain? It's minus GM1 times RDS1 parallel RDS2. Right? What is this? Just divide the output noise by the gain. By the square of the gain. Right? This is the input referred noise. Now what do you want to do? Maximize GM1, which is the amplifier, and minimize GM2, which is the bias transistor. Okay? Suppose you have a load cap. Now, so far we have been looking at, low frequency behavior. Okay. Suppose you have some capacitance. We look at the case where you have an output capacitance. We look at the case where you have an input capacitance. Okay. So let's take this case. Now what is VN out? So same as before. We'll ignore flicker noise again. Okay. This is your total current noise times RD parallel 1 over j omega c whole squared. Right? CL. Okay. So RD squared times 1 over 1 plus omega CL the whole squared. Right? What is the gain now? Again, it turns out gain is also right? Now the gain is also frequency dependent. The output noise is frequency dependent. But because they have the same frequency dependence, the input referred noise is now going to be frequency independent. Okay? Why is this happening? Because you're producing your noise first, and then the output pole happens to come after the noise sources. So, you know, the gain, both the signal and the noise get multiplied by the same transfer function of the output impedance. So the input referred noise happens to be frequency independent. Okay. Now suppose you have an input cap. Okay, suppose you have an input cap. What happens? What will Vn in squared be? What is Vn in squared? You're going to have this source, right? You're going to have ID squared. You're going to have 4kT over RD. Here you're going to have 4kT gamma GM. What is the gain of the circuit? GM squared RD squared, the same as before. So Vn in squared is going to be the same as the normal common source. What's the difference? What's the catch? Something has to be different, right? No, capacitor is noiseless. It's an ideal capacitor, right? A capacitors and inductors don't add noise. What's the difference? Anybody? Of course, you have added a capacitor, there has to be something different, right? Which current? Are you talking about the noise current? Now you actually have an input current noise. In the earlier case, we only had an input referred voltage noise, right? Because we assumed low frequency, the MOSFET has no input capacitance. Okay. When you have no input capacitance, there cannot be any input referred current noise. right? It's an infinite input impedance. Okay, you only have the input referred voltage noise. In this case, now that your input impedance of your circuit has changed, there is actually a frequency dependent input impedance. Now you can actually calculate an input referred current noise. Okay. Okay, so now let's try to calculate what that is. How do we calculate that? We open circuit the input, right? That's how we always do. Open circuit the input, calculate the noise in the two cases, and equate them. Okay. What is VGS squared? Correct? So noise current flows through Cn. What is the noise voltage? It's IN in times 1 over mod of 1 over j omega Cn. So VGS squared, okay, times Gm squared RD squared is the gain now. Gm squared times this times RD squared. That is the output noise mean squared voltage. What is the actual Vn out squared? For kT gamma Gm is a thermal noise current from the transistor plus, I'll call this GD, 4 kT GD, that's a noise from the resistor, times RD squared. Okay. So now we can equate these two. Okay, one is with the input referred noise source, the other is with the actual noise sources in the circuit. What is this? You get a 4 kT gamma over Gm. You get this expression. Okay. 4 kT gamma over Gm plus 4 kT over Gm squared RD, whole thing times omega Cn the whole squared. And of course now if you look at low frequencies, this term goes to 0. Or if your input capacitance is very small. That makes sense, right? How about the common gate stage? What do you expect for the common gate stage? For the Vn squared, In squared. First of all, will it have an In squared? In squared? No, the common gate will not. Why not? So will the common gate have an ion in squared? It will, right? Because for the common source we didn't have it because input impedance was infinite. In this case it's very low, so you would actually expect a higher ion in squared. Correct? Okay. So I mean, now I hope you can directly virtually see what's going to happen, right? You don't have to redraw for these simple circuits, you don't have to redraw the equivalent again and again, right? What is the noise current from this? ID squared. What is the noise current from this? 4kT over RD. Correct? What is the output impedance? RD. Correct? So you can start doing, open circuit, short circuit and so on and look at what happens directly. So suppose you want to find out Vn in short circuit the input, right? Output noise is 4kT gamma GM plus sorry. Okay. What is this? If you had the noise voltage source here, what will that be? Suppose you had Vn in squared. What is the input current? What is the input impedance? 1 over Gm plus GmbS. Okay. So the input noise current power is going to be Vn in squared over Gm plus GmbS the whole squared. Correct? Times RD squared is the output noise voltage. Okay. And in this case we are all calculating the noise voltages. Like we did last class, you can short the output to ground, calculate the short circuit noise current. It will give you exactly the same result because right now, all the noise current is flowing through RD and you're multiplying everything by RD squared, it's getting cancelled over. If you do this, all the noise current will flow through the output. You won't have this term, you won't have this term, and you'll still get the same expression. Okay, there won't be any difference. So this is the expression for your input referred noise voltage source. Okay. Now let's say you open circuit your input. This is open. Now what do you expect for the output? If you calculate the output noise voltage, what do you think it will be? So what happens to this noise? So 4kT over RD, the noise current, flows through the output. What is the output? Output impedance is RD. So that's going to create a voltage 4kT over RD times RD squared, which is 4kT RD delta F. So that is definitely how about the transistor noise? In this case, what's going to happen is the transistor noise is just going to circulate inside the transistor. None of it is going to go to the output. None of it is going to go to RD because you have to have, because here now you're open circuiting it, KCL needs to be valid at both of these nodes. At this node, noise current flows like this, so there should be an equal and opposite noise current flowing here. Okay? That means at this point, if you apply KCL, you have two equal and opposite noise currents, so none of it flows through RD, which is the output resistance. So there is no component, the noise voltage, the noise current from the transistor does not flow through the output. So this is just 4 kT RD delta F. Okay? Now if you have an input referred noise current source at the input, what happens? All of that noise flows through the output. So you had a current source here. What happens? All of that current flows through the output and gets multiplied with RD. Okay? So your input referred noise current is just 4 kT over RD. Okay. So what do you notice about this actually? What do you see? What is 4 kT over RD? It's the noise of the thermal noise of the resistor. What you are seeing is that noise is completely appearing at the input. Right? That you have never seen before. So this happens because the current gain of your MOSFET is actually 1. Okay. So what happens is whatever noise current you have at the output directly gets reflected at the input. Right? So which is not something you see in the common source. Okay. Okay. Now, suppose you have a current source. Suppose you have some bias. Suppose you are now biasing this common gate with a current source. Okay. So what's going to happen now? The noise from these two you have already calculated, that's not going to change. What about the noise from M2 and M3? Okay, let's consider first M3. What is going to happen to the noise from M3? So let us say it has some 4 kT gamma GM delta F. What's going to happen to that noise? Will you see that at the output or not? Any ideas? Sorry? Perfect. So because of the current mirror action, so this noise voltage, this noise current will produce a noise voltage here, which is going to produce a noise current here, and it will preserve this mirror ratio. Okay? So the noise will get multiplied up by n times, or n squared times, the mean squared noise, sorry, the squared noise will get multiplied by n squared to this node. Okay, so that current is going to flow through this. Now suppose you are interested in finding the input referred noise voltage. What do you normally do? You short the input. Correct? What is going to happen? All this noise current is going to flow through the shorted input. None of it appears at the output. Okay. In other words, noise from M2 and M3 is not going to affect, and M3 will be in parallel with that, just adds to that. So it's not in a different case, but all that noise will flow into the short circuit. So in other words, your input referred noise voltage is going to be the same as before. Correct? Okay. Now suppose next you open circuit this. Now that both those noises are going to flow directly into the output. So you'll have the old input referred noise current, or whether Vn out squared when you are calculating the input referred noise current, and you would add the noise of M2 and the multiplied up noise of M3 to that times RD squared. You will have to do that. Okay. What can you do about M3? So one thing you can do, which people often do, is to add a capacitor here. What happens? This capacitor shunts any noise from M3 to ground. Okay? So that noise from M3 gets shunted to ground and it doesn't get multiplied up. Okay? This is something you can do to get rid of M3 noise. What do you do about M2 noise? Nothing much can be done. Okay? One thing you can do is, this noise current is 4 kT GM2, 4 kT gamma 2 GM2 delta F. So you would try to minimize GM2. Remember, it's now a biasing transistor, so you want to minimize the GM. Right? When you try to minimize the GM, what happens? The headroom, the VD SAT of the transistor goes up for a given current. So the current bias does not change because you want to bias the common gate with a given current. Correct? You want to bias the common gate with a given current, so that current does not change. For a given current, if you reduce GM, VD SAT goes up. Right? Because you're going to reduce W over L, increase in the current density, so VD SAT goes up. Then what happens? VD SAT, the headroom required for this goes up, so VB has to go up correspondingly, and that means that your outputs now cannot swing as much. So there is a direct correlation between minimizing noise in the circuit and the allowed output swing, the dynamic range at the output. Okay? And if you want the expression, I think, yeah, you can calculate the expression for the current. Okay, it's not a big deal at all. You'll just have noise now from M2 adding directly to the old expression. Okay?